The last big idea we want to look at kind of in our overview notes for this unit is Newton's universal law of gravitation and that connection to orbits. This is a big thing with circular motion that we want to kind of start looking at. So as review, the force of gravity, the equation for that is G m1 times m2 over r squared. You can look up the universal gravitational constant if you want. That's also on your equation sheet. We've talked about this before, and you can use this to find, the strength of a gravitational force acting on an object. One thing that we've talked about before is the strength of the gravitational field, and this is sometimes labeled as lowercase g. And it's basically everything in the equation that might be held constant for a given planet or something. So if we were talking about Earth, it's g times me over r squared, because then if you wanted to find how strong gravity is on a specific object, well, then you would just multiply by, the missing m here. But that's just a side note of if we talk about strength of gravitational field, we're really talking about this kind of g, or this acceleration of acceleration due to gravity. Bringing this into orbits, a stable orbit is one where the centripetal force is provided by the gravitational force. So we'll do an activity with this in class a bit more where we kind of play around with the idea of an orbit. But if we think about it, if the Earth is roughly a sphere, and you've got something orbiting it or circling it and staying at roughly the same height above the Earth, well, that means this is basically a circular path. And so how does it stay in a circular path? Well, it's always being turned or pulled towards the center. And so if that orbit is going to be maintained or be stable, that means that the gravitational force is what's keeping it traveling in that circle. So using what we've learned, we can say that Fg is going to equal to the centripetal force. Fg is big G times mass of the Earth, times, we'll say it's a satellite, so we'll say the radius of the satellite squared, times mass of the satellite. And we know that that has to equal mass of the satellite times the velocity or the speed of the satellite squared over the radius that the satellite is at. We can cancel one of these masses, cancel this r, and we get that the velocity or the speed of the satellite is equal to the square root of g mass of the Earth over radius of the satellite. And you can imagine that, if this was a different planet or if it was higher or lower, you can modify those. But the key idea here is that we see that this is a relationship between speed of an orbit and the radius of the orbit. So in other words, the farther away the orbit is, the farther away from Earth something is orbiting, if it's in a stable orbit, the lower the speed needs to be. If you want to have something travel really fast, it's going to end up being quite close, or if you want to have, the orbit really small, you've got to be traveling really fast. If you want the orbit to be quite large, you don't have to travel as fast. And this is something we'll play around with as time goes on, but I just wanted to introduce the idea and show you how we can kind of connect all of that together here. As always, if you have questions, let me know, but otherwise, that will wrap up kind of the core notes for this unit.